All right, in this screencast, I want to take some time and walk us through a question that has appeared on a final exam I wrote for SUNY Geneseo in Calculus II. The question is posted in our learning management system, which is fine. If not, you can always pause the video here and work through the question. The expectation for me is that this question should take you, the student, about 15 to 20 minutes to do. So you can pause and try it yourself, and then I'll work through what I think the answers are in a moment. So you've had time to read the question. We're going to do a couple of things that are valuable. We're going to do where is the tangent line vertical, and then we're going to do the perimeter of R, and then we're going to talk about the region S. So let's go to work. We're looking for where a tangent line is vertical. So how do you find the slope of a tangent line? Well, the slope of a tangent line is dy d theta over dx d theta. If the tangent is vertical, then this is 0 and this is not 0. So we want dx d theta to equal 0. So what's dx d theta? Well, we have to remember what x is. X is r cosine theta. So dx d theta is derivative of first times second plus first derivative second. And we want to know when this is 0. So how do we find when this is 0? We put this into our calculator in function mode, where we make all the thetas x's because we're in function mode, and then we find where that curve hits the x-axis. And it happens that happens at theta equals 0.823, which sort of makes sense because that would be about here, right? It'd be about there. And we know that this is theta equals 0, and this is theta equals pi over 2. That's 1.5 something. So this is between 0 and 1.5 something. That appears to be reasonable. And so that is the theta we choose. Okay, so now we're looking for the perimeter of R. R is the region bounded by the graph of R equals theta plus sine theta and the x-axis. So R is this region. And so its perimeter is the length of this line segment plus the length of that curve. Well, what's the length of this line segment? This happens at theta equals 0. This happens at theta equals pi, pi plus the sine of pi. Right? So this line segment has a length of pi. And then we have the integral from 0 to pi of the square root of r squared plus dr d theta squared d theta. Remember, this is the r squared. This is the dr d theta squared. Your calculator does this for you, and it ends up. Now, how does your calculator do it for you? You put your calculator back into function mode if you like, and all those thetas can become x's. Your calculator doesn't care what the variable is because calculus doesn't care what the variable is. It doesn't matter what the variable is. Your calculator figures it out just the same. So you get 2 points for knowing that you have to integrate something from 0 to pi. You get 2 points for knowing what this is. And then you get 2 points for finishing the thing off with the length of that line segment in play. So the ray divides the region S into two regions of equal area. Write an equation involving one or more integrals whose solution is this value of k. So what in the world is happening here? We imagine that if you divide by some ray, all the area from here to here, all the area from here to here, that's the same area on this side of the ray as on that side of the ray. What do we have to know? Well, the region S is this semicircle with that area taken out. So we have to know what that area is. The area of the region R is the integral from 0 to pi of 1/2 r squared d theta. And any calculator will tell us what that area is. So when we're looking for the area of S, well, S is a semicircle whose radius is 4, minus this area from the other part, and that's about 16. So when we do the integral from 0 to k, the integral from 0 to k has to be half of that number. We are going to integrate from 0 to k. But what? Well, there's a big area to integrate minus a small area to integrate. The big area is 1/2 r squared. The little area is 1/2 r squared d theta. Big area is 1/2 r squared d theta. The little area is 1/2 r squared d theta. And if we solve this equation, we will get the value of k that we're looking for. So breaking this up at theta is k, we integrate from 0 to k, we get an integral that gives us half the area of the whole region S. And then we remember that to integrate to find area, we do 1/2 r squared, 1/2 r squared, and subtract the results. This is a fairly standard kind of a polar free response. And I hope that my answers are helpful to you as you prepare similar questions for our final exam.